Good day, everyone. Today, we will be discussing a fascinating historical and mathematical problem related to the distribution of representation in the U.S. House of Representatives. The issue that we will be discussing is known as the apportionment paradox, specifically focusing on a notable example called the Alabama paradox. The Alabama paradox was the first apportionment paradox to be discovered. The U.S. Constitution requires the House of Representatives to allocate seats based on population counts from the census, which is conducted every 10 years. The total size of the House is set by law, meaning the number of representatives must be divided among the states based on these population counts. But how do we fairly decide how many representatives each state should get? This question has been the subject of debate for centuries. One of the proposed solutions came from Alexander Hamilton in 1791. He developed a method to apportion representatives among the states. While this method was approved by the Congress, it was vetoed by President George Washington. However, Hamilton's method was later adopted in 1852 and used until 1911. After the 1880 census, Charles Seaton, the chief clerk of the United Census Bureau, was tasked with calculating the apportionment for various possible house sizes, ranging from 275 to 350 representatives. During this process, it was discovered that with a house size of 299 members, Alabama would receive 8 seats. However, if the size of the House increased by just one member to 300, Alabama would lose a seat and receive only 7 representatives. This unexpected result is known as the Alabama paradox. Why does this matter? The paradox occurs when increasing the total number of items, such as seat in the House, result in one of the parties or state receiving fewer seats. Another example happened in the 19th census, when Colorado count dropped from 3 to 2 with a total of 357 House members. These paradoxes highlights the complexities and challenge in achieving fair representation, something that is still relevant today as we continue to find ways to manage representation.
The apportionment paradox is the phenomenon wherein modifications to the distribution criteria or the total quantity of things to be distributed produce unexpected or illogical outcomes. This is frequently observed in the distribution of legislative body seats where various approaches can have multiple results. Key paradoxes include the Alabama paradox, where an increase in total seats results in a state losing a seat. The population paradox, where a larger state gains fewer seats due to the apportionment method. The new states paradox, where a new state may lead to existing states losing seats despite constant populations. And the quota paradox, where the calculated quota for a state is not reflected in the final apportionment.
Next, we have the definition of terms. Apportionment is the act of dividing items between different groups according to some plan, especially to make proportionate distribution in a fair manner. Apportionment paradox occurs when a change in the total number of items to be apportioned or change in a distribution criteria leads to an unexpected or counterintuitive result. Quota rule is a desired property of a proportional apportionment methods. Standard divisor is the total population divided by the total number of seats. Standard quota, also called exact quota, is the number obtained by dividing the state's population by the standard divisor.
Next is the steps and procedures. The first one is you need to calculate for the standard divisor. The standard divisor is calculated by dividing the total population by the number of items or seats to be allocated. The second step is find each state's standard quota. Divide the population of each state by the standard divisor. This is the number of voting seats each state should receive. The third one is you need to assign the lower quota to each state. So you need to rounding down the standard quota to an integer gives the lower quota, and rounding up gives the upper quota. The last is you need to adjust the final answer. The final number of seats allocated to each state is adjusted based on the sum of the lower quota, which are rounded down values of the standard quotas.
In this scenario, we have a country with 4 states and 30 seats at Congress, and the population of the states are given, and the goal is to distribute the 30 seats proportionally based on each state's population. This is our sample problem. The following is a simplified example following the Hallmanson method. In solution, first, calculate the total population, divide the total population and the 30 seats in Congress, which result to 6,300, and easy way to explain, state A divide the total population and the 6,300, which result to the quota. Then, assign initial representative. The initial number of representatives for each state is obtained by taking the floor of each state's quota, rounding down the nearest whole number. This gives us 29 seats, but we need to assign a total of 30 seats. We need to adjust the final representation since we need to assign 30 seats in total and currently have 29. We give the extra seats to the state with the largest fractional part of this quota. Since state A has the largest fractional part, it received the extra seat.
Interpretation and answer. So that is the final answer for the given sample problem as 30.
Paradoxes and apportionment reveal the complexities and potential unfairness in legislative seat distribution methods. These paradoxes highlight that mathematical formulas designed to ensure fair representation can sometimes produce unexpected results. Understanding these paradoxes is crucial for evaluating and improving apportionment systems to reflect population changes and ensure equitable representation. The chosen methods significantly impact political power and fairness, suggesting ongoing assessment and potential reform to align them with equity and democracy principles.